In this video, I will present the 1977 Gibbard theorem and its consequences. The Gibbard theorem is a characterization of so-called strategy-proof voting systems as convex combinations of strategy-proof unilaterals and duples. And as a corollary, the only unanimous, anonymous, and strategy-proof voting system is random dictatorship, also known as autocracy. Namely, each voter casts a ballot with the name of his favorite alternative, and one ballot is drawn randomly. The alternative whose name is on this randomly drawn ballot is the election winner. Let's see what this all means. First, we consider a set n of voters and a set m of alternatives. A preference theta naught or in O is a total order of m, and a preference profile is an n-tuple, theta equals to theta 1 until theta n in O to the power n. A deterministic vote would then be a function v that goes from O to the power n to m, but the thing with the 1977 Gibbard theorem is that it also considers randomized votes, that is functions v from O to the power n to r to the power m. That is, we're going to be able to measure vj of theta, which is the probability of electing alternative j when preference profiles are theta in On. Evidently, v of theta, which is the vector v1 of theta until vm of theta of r to the power m, is actually a probability law, which means that it must belong to the so-called simplex of Rm. That is, it must satisfy the properties vj of theta greater or equals to 0 for all j in m, and the sum of the vj of theta must be equal to 1. Now, to understand the Gibbard theorem, we need to define strategy-proofness or incentive compatibility. These are the two equivalent terminologies in the literature. But because here we have uncertainty, we have some randomness, it's going to be a bit hard to define strategy-proofness. It's not going to be as straightforward as it was for the Gibbard Flatterthwaite theorem. A voting system V is strategy-proof if for any preference profile theta in On, any voter I in N, any ballot AI in O, so far it's the same as strategy-proofness in the deterministic setting. But now we need to consider any von Neumann-Morgenstern preference hat of theta I that is consistent with theta I. Then for any such von Neumann-Morgenstern preference, we must have hat of theta I that necessarily prefers V of theta to V of AI theta minus I. But interestingly, because of the von Neumann-Morgenstern theorem, these von Neumann-Morgenstern ordinal preferences over lotteries can be equivalently understood in terms of utility functions. So equivalently, we can restate strategy-proofness as follows. A voting system V is strategy-proof if for any theta I and AI, and for any vector ui in Rm, that corresponds to a utility function description of the von Neumann-Morgenstern preference hat of theta I. If ui is compatible with theta I in the sense that if theta I says that j is better than k, then the real number uij must be greater than uik. And if we have that for all jk, then strategy-proofness implies that the expected utility according to v of theta, that is the sum of the uij vj of theta, must be greater or equal to the expected utility when voter I casts ballot AI, that is the sum of the uij vj of AI theta minus I. So this is very cumbersome. Fortunately, this cumbersome condition boils down to a much simpler one known as stochastic dominance, which corresponds to saying that if you consider a preference theta I that says that ji is better than j2 until jm, well, the j or k are all different, then for all k in m, we must have that the probability of the k best alternatives according to theta I, that is the sum of the vjl of theta for L going from 1 to k, well, the probability of these top k candidates must be greater when voter I casts ballot theta I than when he casts ballot AI. That is, it must be greater or equal to the sum for L going from 1 to K of VJL of AI and theta minus I. Gibbard's tour de force was to find a simpler equivalent characterization of voting systems that satisfy stochastic dominance. Namely, he proved that strategy-proof voting systems were convex combinations of unilaterals and dupoles. So what are these? Well, a unilateral voting system U is a voting system, so it goes from O to the power n to R to the power m. And the outcome of this unilateral, possibly randomized voting system is actually a function of a single voter's ballot. That is, U is unilateral if and only if there is a dictator, let's call it I, and a function f that goes from O to R to the power m, such that for any preference profile theta, V of theta is actually equal to f of theta I. It does not depend on other voters' preferences. Prototypical example of unilateral voting systems is dictatorship. You can have other unilaterals. For instance, instead of electing voter I's top candidate, you can elect his two top candidates with probability 1/2 each, or you can have more complicated stuff like that. But importantly, the outcome only depends on voter I's preferences, on the dictator's preferences. So that's a unilateral. What's a dupole? A dupole is a function d from O to the power n to R to the power m. So it's still a randomized voting system. But a dupole needs to have a support that is restricted to two alternatives. In other words, V is a dupole if there are two alternatives J and K, such that for all preference profiles theta in ON and alternatives L different from J and K, we must have VL of theta equals to 0. No alternative different from J and K can be elected under a dupole. We can finally state Gibbard's theorem. If V is strategy proof, then there must be unilaterals U1 until UK and dupoles D1 until DL, as well as probabilities P1 until PK and Q1 until QL, such that, well, these are probabilities, so this means that the sum of all the PK and QL must be equal to 1, and V is then a sum of the PK UK and the QL DL. In other words, it's a convex combination of the unilaterals and the dupoles. Now, there's an easy corollary of this theorem, which is the equivalence that I stated earlier, namely V if strategy proof, if and only if there are strategy proof unilaterals U1 until UK and strategy proof dupoles D1 until DL, as well as probabilities P1 until PK and Q1 until QL, such that the sum of PK plus the sum of QL is equal to 1, and V is equal to the sum of the PK UK and the sum of the QL DL. Let's now see what happens when we include additional properties. We'll say that V is unanimous when if J is every voter's top choice, then V must elect alternative J with probability 1, that is Vj of theta must be equal to 1. And we'll say that V is anonymous when all voters are treated the same way, i.e. for any permutation sigma in Sn, V of theta must be equal to V of theta sigma 1 until theta of sigma of n. That is, no voter can have a different influence on the outcome than another voter. A corollary of Gibbard's theorem is that if there are at least m greater than or equal to 3 alternatives, and if V is strategy proof and unanimous, then it is a random dictatorship. That is, the probability of election of alternative J is the sum of the weights of voters whose top choices are alternative J. Indeed, this is because dupoles are not unanimous, and the only unanimous strategy-proof unilaterals are the ones that elect the dictator I's top choice with probability 1. In other words, for m greater or equal to 3, any strategy-proof and unanimous voting system must be written as V equals to the sum of the Pi, Ui, This corresponds to saying that any voter I has a probability Pi of becoming the dictator, in which case the voting system V elects voter I's top choice. Finally, if we demand in addition that the voting system be anonymous, that is, if we demand every voter to be treated equally, then we must have Pi to be the same for all voters, that is, Pi equals to 1/n for all voters I in n. In such a case, we now have a single possible voting system V, which is V equals to 1/n times the sum of the UI, i.e. random dictatorship with uniform distribution over voters.